Well, what I know is that I attempted to call their attention after the report came out. I looked at it, and, it had a physical form but also exists online. You can search for it, and I could see that ticks, mice, and rodents weren't mentioned. So, I tried to alert them to the fact that they had made a mistake. Joe Rogan has done it again. He recently revealed a shocker making waves on his famous podcast, The Joe Rogan Experience. Scientists have released something into the United States without the public's knowledge. From secret experiments to unintended side effects, we will unravel the truth behind this jaw-dropping revelation. You won't want to miss this. Lyme disease *. Imagine enjoying a beautiful day outdoors, only to later discover a tiny, unwelcome hitchhiker, a tick. But not just any tick, as you'll soon see. This small creature can carry a big problem, Lyme disease. Lyme disease is a serious illness caused by bacteria transmitted through the bite of an infected blackleg tick, commonly known as a deer tick. These ticks are prevalent in wooded and grassy areas. How do they get infected? These ticks often feed on a certain species of mice, key carriers of the bacteria. We'll discuss more in this video. The impact of Lyme disease on public health is significant and has been a cause for concern for the Centers for Disease Control and Prevention, CDC. In the United States alone, the number of reported cases has steadily increased. According to the CDC, over 63,000 cases of Lyme disease were reported in 2022. However, recent estimates suggest that approximately 406,000 people are diagnosed and treated for Lyme disease each year in the United States. A scarier reality *. In some circumstances, Lyme disease can be fatal. Between 1985 and 2019, 11 reported fatalities occurred worldwide due to Lyme carditis, a heart condition linked to Lyme disease. This demonstrates that Lyme disease can be deadly, and there is a possibility that the number of fatalities could be underreported, a major problem. Underreporting complicates efforts to understand the true prevalence of the disease and disrupts public health initiatives aimed at controlling its spread. Even when cases are reported, misdiagnosis occurs due to a lack of awareness among healthcare providers and the public, hindering early detection, rapid diagnostics, and effective treatment. Misdiagnosis often arises because Lyme disease symptoms, which can be debilitating and vary among individuals, mimic those of other illnesses. Early signs include fever, headache, fatigue, and a characteristic skin rash called erythema migrans, or the bullseye rash. If untreated, the infection can spread to joints, the heart, and the nervous system, leading to severe complications like arthritis, heart palpitations, neurological issues, and, in the worst cases, death. The chronic nature of these symptoms can significantly impact a person's quality of life, making early detection and treatment crucial. The disease affects not only the lives of those infected but also places a substantial burden on the healthcare system. The costs associated with diagnosis, treatment, and long-term care for Lyme disease patients are considerable. As more people are diagnosed, the demand for medical resources and public health interventions continues to skyrocket. The cause *. All of these issues stem from mice, ticks, and bacteria. The origin of Lyme disease traces back to the white-footed mouse, *Paramyscus leucopus *, a small, seemingly harmless rodent with distinctive white feet and large eyes. These cute forest dwellers are the primary carriers of the bacterium Borrelia burgdorferi. When deer ticks feed on these mice, they pick up the bacteria, which they then transmit to humans and other animals. Mice play a critical role in Lyme disease transmission, with areas abundant in these mice experiencing higher incidences of Lyme disease. This is why Lyme disease cases have risen in regions like the northeastern United States. While eliminating the mice would help, it's not an easy task. If it were, their population would have significantly decreased, as Lyme disease has been a recognized health issue in the United States since the 1970s. The disease was first identified in Lyme, Connecticut, in 1975. When a group of children and adults began experiencing strange symptoms like swollen knees, paralysis, skin rashes, headaches, and severe chronic fatigue, renowned Dr. Alan Steer and his colleagues described this phenomenon as Lyme disease after investigating the symptoms. Dr. Steer and his team conducted extensive research and identified a pattern linking these symptoms to tick bites. Lyme disease patients often suffer from long-term symptoms due to an immune system marker found in the blood. This groundbreaking work led to identifying Borrelia burgdorferi as the causative agent of Lyme disease, which was officially classified in 1981. Despite being discovered in the 1970s, Lyme disease and the bacteria responsible were relatively new discoveries. Research has shown that the bacterium behind Lyme disease has been present in North America for thousands of years, though its prevalence only significantly increased due to ecological changes such as forest fragmentation and the population growth of deer ticks, which created ideal conditions for these ticks to thrive. The identification of Lyme disease as a serious health issue in the 1970s marked a turning point in understanding tick-borne illnesses. Before then, symptoms in infected individuals were often misdiagnosed as other conditions. Since then, thousands of new cases have been reported in the United States alone. The discovery of Borrelia burgdorferi allowed for more accurate diagnoses and treatments. Following this breakthrough, scientists addressed Lyme disease with a broader approach. Initially, public health initiatives focused on raising awareness, promoting preventive measures, and ensuring access to accurate diagnosis and effective treatment. Additionally, scientists implemented ecological management strategies essential to reducing the risk of tick-borne diseases. However, despite these efforts, further actions were needed. Increased focus was placed on studying, understanding, and diagnosing Lyme disease more accurately, leading to yet another breakthrough in developing diagnostic tests like the enzyme-linked immunosorbitassay, ELISA, and Western blot. At first, antibiotics such as doxycycline, cefuroxime, and amoxicillin were the primary treatments for Lyme disease, administered for 2 to 4 weeks depending on the infection's severity. Early treatment with these antibiotics proved effective in preventing disease progression and more severe symptoms. However, despite antibiotic effectiveness in treating early-stage Lyme disease, many patients who visited their regular doctors did not always receive effective treatment. Some patients continue to experience symptoms even after completing treatment, a condition known as post-treatment Lyme disease syndrome, PTLDS. PTLDS is characterized by persistent symptoms like fatigue, muscle and joint pain, and cognitive difficulties. The exact cause of PTLDS remains unclear, and there is no consensus on managing these lingering symptoms. As a result, increasing public awareness became essential. The CDC launched awareness campaigns to educate the public on Lyme disease, its symptoms, and preventive measures. These campaigns highlighted the importance of avoiding tick bites by using repellents, wearing protective clothing, and conducting regular tick checks after outdoor activities. For those walking in grassy or wilderness areas, wearing long sleeves, long pants, and socks with shoes is advised. While these CDC initiatives were critical, research continued, and in the late 1990s, a significant advancement emerged: the first Lyme disease vaccine, LYM-Erix, developed by SmithKline Beecham, now GlaxoSmithKline. The vaccine worked by stimulating the immune system to produce antibodies that attacked the Lyme bacteria in the tick's gut before it could enter the human body. Unfortunately, the vaccine was a short-lived victory. Due to low demand and concerns about side effects, it was withdrawn from the market in 2002. So, what came next in the fight against this relentless disease? It seemed that little significant action followed. Had the scientists given up? On Joe Rogan's podcast, The Joe Rogan Experience, which boasted 14.5 million followers on Spotify as of late March 2024, Rogan discussed a controversial leak from an anonymous hacker. This hacker revealed that scientists have been working secretly to address the Lyme disease threat. According to the hacker's claim, scientists at a prestigious research institute in Massachusetts have been tirelessly working on a secret project called Mice Against Ticks, which aims to combat Lyme disease. The hacker's documents claimed that this project involved releasing hundreds of thousands of genetically engineered white-footed mice into the wild. These mice were designed to reduce tick populations and thereby curb Lyme disease transmission. The revelation is both startling and ethically complex. Releasing genetically modified organisms into the environment without public knowledge or consent is controversial. Moreover, altering one species could trigger unforeseen ripple effects in the ecosystem, impacting other wildlife and plant species. Still, one might argue that the scientists' efforts are not entirely unprecedented. Genetic modification has previously brought about beneficial impacts, especially in medicine. For instance, a breakthrough in the late 1970s led to the development of artificial insulin to treat diabetes. Traditionally, insulin was extracted from animals like pigs and cows, but this approach had limitations, such as supply shortages and allergic reactions in some patients. In 1973, scientists Herbert Boyer and Stanley Cohen introduced a revolutionary method by transferring genes between organisms, using E. coli bacteria to produce human insulin. This achievement made insulin production safer, more accessible, and affordable for millions worldwide, revolutionizing diabetes treatment. In the 1980s, scientists developed transgenic mice, genetically modified to carry genes from other species. These mice became invaluable tools for studying human diseases like Alzheimer's and cancer, providing crucial insights for testing new treatments. From the scientists' perspective, genetic engineering has repeatedly yielded positive outcomes, and they hoped for similar success with their genetically modified white-footed mice on Nantucket Island. These mice were specifically engineered to combat Lyme disease by reducing the tick population, aiming to curb disease spread at its ecological source. The genetically modified mice possess the capability to disrupt the life cycle of ticks, reducing the incidence of Lyme disease. According to leaked documents, the scientists released approximately 100,000 genetically engineered white-footed mice in carefully timed batches over the course of a year. Every 2.5 months, new groups of 20,000 to 40,000 mice were introduced to ensure a gradual integration of disease-resistant genes into the wild mouse population. The goal is to create a robust population of Lyme-resistant mice that can pass on their resistance to Borrelia burgdorferi, the bacterium causing Lyme disease, thus reducing infected tick numbers and ultimately lowering human infection rates. Nantucket, an island off the Massachusetts coast with a high Lyme disease prevalence and a relatively contained ecosystem, was chosen as the experimental site. Since 2019, the island has recorded over 500 confirmed cases of Lyme disease. The isolated nature of Nantucket allows for controlled observation of the mice's impact on the environment, without the additional variables a mainland environment might introduce. The success of this project will take time. As the genetically modified mice breed, the researchers anticipate that resistance to Lyme disease will spread within the wild mouse population, gradually reducing the number of Lyme-infected ticks. Monitoring efforts will focus on observing how these mice interact with their environment and other species, ensuring that their introduction doesn't disrupt the natural balance. Data collected on the tick infection rates in human Lyme cases will help determine the experiment's effectiveness and guide adjustments as needed. If successful, this Nantucket experiment could inspire similar initiatives in other regions affected by Lyme disease and set a precedent for using genetic engineering to combat vector-borne diseases like malaria and Zika virus. The concept originated from a Massachusetts Institute of Technology professor who proposed it to the Nantucket Board of Health, sparking the project's initiation. The implications extend beyond public health, raising broader questions about the societal and ethical boundaries of genetic engineering in scientific innovation. The release of genetically modified mice on Nantucket to combat Lyme disease has stirred both support and concern among locals. Although about 24 residents initially expressed their support for the project, questions remain about the extent of their understanding of the potential ecological and ethical implications. The concept of releasing tens of thousands of genetically engineered mice has raised concerns about possible ecological imbalances and unintended consequences. One major worry is the potential disruption to the food chain. White-footed mice serve as both predator and prey in their habitat, and altering their disease resistance and possibly even behavior could create a super-predator scenario. If the genetically engineered mice become better hunters, they could outcompete wild mice for resources, leading to the decline of other prey species. This decline could create a ripple effect throughout the ecosystem, affecting predator species that rely on the mice's prey for survival and potentially leading to a loss in biodiversity. Additionally, with their natural food sources diminished, these modified mice might seek out alternative food sources, possibly even moving into human dwellings and public spaces in search of sustenance. Such interactions could not only create nuisances but also health risks, as mice are known carriers of various diseases. The risk of gene flow is another concern. If disease-resistant genes spread to other rodent species, it could disrupt natural ecological relationships, creating new dynamics that are difficult to anticipate or control. Genetic modification may also impact biodiversity by reducing genetic diversity within the white-footed mouse population, potentially making it more susceptible to future diseases and environmental challenges. There is also a significant social and ethical dimension to consider. Public opinion on genetically modified organisms, GMOs, varies widely, with many people concerned about the long-term consequences. Engaging local communities in meaningful discussions can help address these concerns and build support for future steps. Effective regulation and governance are crucial in overseeing the release of genetically modified organisms, including comprehensive guidelines for ongoing monitoring, data collection, and adaptive management to mitigate any unforeseen consequences. The project's success could bring a sustainable solution to Lyme disease prevention, but it also underscores the need for careful consideration of ecological, social, and ethical factors in deploying genetically engineered organisms. The broader implications for genetic engineering in public health continue to fuel debate, highlighting the balance between scientific innovation and ecological preservation. The Lyme disease prevention project on Nantucket is, indeed, a bold scientific undertaking, fraught with both promise and uncertainty. Scientists involved believe the potential health benefits, such as a reduction in Lyme disease cases, justify the experimental risks. Despite ecological concerns, ethical debates, and logistical challenges, they remain committed to the project, maintaining careful oversight of the released mice and collecting data to assess its effectiveness. The global regulatory landscape presents another hurdle, as creating and enforcing specific regulations around genetic modification varies widely between regions. However, the researchers' perseverance stems from a clear public health need. With Lyme disease posing a growing health risk in many areas, they hope that this innovative approach, though speculative, could eventually lead to a breakthrough. This project is an ambitious test case for using genetically modified organisms, GMOs, in disease control, and it brings to light the delicate balance between scientific progress and ecological stewardship. As monitoring continues, the data gathered will be crucial in determining whether this approach can indeed pave the way for safe, effective, and sustainable disease prevention strategies for Lyme disease and potentially other vector-borne illnesses in the future.